Hello, everybody. This is the Life History Strategy Lecture, and I think we should start off with defining what life history is. Life history is basically a schedule of where organisms put their energy, or what type of adaptations these organisms have that allow them to do certain things. So, what we know is that an organism cannot maximize all life history's traits. Now, what does that mean? So let's think about an example here. Penguins, super good in water, right? They are amazing swimmers that are just like little torpedoes that can speed through the water at, 30, 40 miles an hour. Crazy fast how the biggest penguins can go. Penguins, though, are not good on land, and they're even worse in the air, right? They cannot fly. Whereas a peregrine falcon is this amazing flyer that can dive at speeds of 300 miles an hour, can fly straight line speeds of like 70 or 80 miles an hour, I think, for a very long time. Crazy how fast and how good flyers they are. But they're not really that great on land, and again, they're terrible in the water. So there's trade-offs, right? Depending on what environment these organisms are living in, well, any organism is living in, I should say, there's trade-offs. You cannot be good at everything. Maybe an example of this is American football, right? So a lineman is 300 pounds, does not make a good quarterback, does not make a good running back that needs to be very fast and run around. You can be strong, like a bear, but not very fast. A cheetah can be fast, but not very fragile. Another way to think about this has to do with how many babies you have and how much energy you put into them. It's impossible for organisms to have 100 babies and care for them all the same that like a human would, right? That just doesn't work. So what we see is organisms kind of shift one way or the other into different types of strategies. An example of this are these different strategies is the opportunistic strategy. Okay, these are organisms that are small. They're generally don't live very long. They develop very quickly and they have lots of babies, but they don't care about their babies, right? They don't care for their babies, I should say. So when think about maybe late May, early June, you'll see these tiny little baby bunnies coming out about the size of a baseball. And you're like, oh, look at the baby bunny. It got kicked out of its nest. But a bunny that size, it's the size of a baseball, is ready to be on its own. Yes, a lot of them are going to get eaten by foxes, by hawks, by eagles, by lots of different things. But rabbits, what they do is they take a different strategy. They put a bunch of energy into having a lot of babies and then just hope some of them survive. And it turns out they do survive and they're just fine, right? Dandelions are the same way, right? They make these tiny little seeds that float up into the air and hope that one of the seeds makes it to a good spot. Most of those seeds will fly into a cement and get smooshed or dried up and don't go anywhere. But if one of those seeds makes it, then that plant did its job. Now, on the other side of the spectrum then is the equilibrial strategy, where organisms develop slowly. They have fewer offspring, lots of parental care, and really long-lived. So humans are this, elephants are this, monkeys are this, primates. A baby monkey will stay with its mom for maybe up to a year, maybe, and that's a long time for a monkey that might only live to be 4, 5, 6, 7, 8 years old. If they're with their mom for that percentage of their time, that's going to take a lot of energy. So but how do plants do parental care? It has to do with that size of the seed. So a whole coconut is actually one seed. That's what it is. It's the seed for a coconut palm tree. And you think of how much energy is in a dandelion seed versus how much energy is in a coconut. And obviously there's a ton of energy in that coconut. And the reason why that is because coconuts are, think about them on a beach on this deserted island, right? So the coconut falls off the tree and plops into the water. It gets taken to a new beach. The coconut lands on that beach and it needs to grow. Well, it's just on a beach with sand and there's no nutrients. So it really needs to have a really good big head start by energy from the seed, from the coconut. And the plant can actually grow relatively large before it needs to be doing things on its own because it has so much energy in that seed. Now compare that to a dandelion. A dandelion, most of those seeds are going to germinate, sprout, and get killed off right away. But one that lands in a good place, a nice open bare patch of lawn that someone just dug a hole or something, there's plenty of nutrients and it doesn't need to get very big before it can get plenty of nutrients from the ground around it. So equilibrial strategy is a great strategy for organisms to use. So you might ask the question, or I could ask you the question, which is better? That opportunistic where you have a bunch of babies and some of them die, or a lot of them die, or put a lot of energy into 1, 2, 3 babies throughout your whole lifetime and they probably will survive. And a lot of people lean towards that idea that the equilibrial strategy is better. But we still have rabbits, we still have oysters, we still have all sorts of different organisms. So really it depends on the situation. Think about a really unstable environment where, let's say, oysters that are on this rock here in this crazy big crashing wave kind of situation. So let's say an oyster were to take that equilibrial strategy. It grows its baby, it makes a really big baby, puts a lot of energy and time into growing this baby, releases it out into the water, and a wave comes and bashes it against a rock and kills it instantly. Okay, that was a whole bunch of wasted effort and that didn't work, right? So what we see is oysters don't take that strategy. What they do is they've evolved to have tiny little babies, single celled eggs that are very, very small. They get fertilized and the larvae go into the water, and yes, millions of their babies get killed, but one of them will probably find a way to attach to a rock and be okay there. Whereas, think about so in an unstable situation, the opportunistic strategy is probably better. But in a stable environment, so this nice little city pond where, nothing is really going to happen, those geese here, they can only have a couple babies here. What do they have? 6 little baby goslings there that are going to grow and will be just fine. They can put a lot of energy into just those 6 babies. Now 6 might seem like a lot, but it's nothing compared to an oyster that would have 1 million babies. So they can put a lot of energy into those small number of babies, and then most of them will survive to adulthood and then have babies of their own. So, I've kind of casted this as a very opportunistic or equilibrial, but honestly there's kind of a continuum where we have many types of babies or many types of strategies in between here. There are organisms that put a medium amount of effort into a medium number of babies. Think like squirrels. Okay. One thing that how we can see this really play out has to do with the size of the individual and the number of individuals. So, the bigger the baby is, the fewer number they're going to have. So an orangutan or humans are going to be way out here. Humans are naturally very rarely have twins or triplets. Twins can be common. They're still relatively rare. but triplets and quadruplets and anything above that is pretty much not naturally occurring. So, but then, an oyster or a mosquito is on this side, or rabbits, might be down here, where the babies are very small, but they can have then a lot of them. What we see then is the baby size, the size of the individual offspring really has a big impact on the probability for it actually surviving. The bigger the baby starts off with, the better head start it has, and the higher the probability is that it will survive. So we can see this is the size of offspring really is has to do with parental care. The bigger the babies are, the more parental care. Orangutans will stay with their mother for like 6 to 8 years, I think. And whereas an oyster baby will, essentially spend 0 time with their parents, and their parents do not care for them at all. Now, another way we can think about life history strategy, rather than so much about reproduction, I guess this is about reproduction too, but what we see is there's 2 different strategies that organisms take when they're speaking about growth. So the first one is determinate growth. So this is where basically organisms stop growing once they start reproducing. And this is what we see with humans, right? Once you start to hit reproductive age, your growth rate slows down, and rather than I guess I shouldn't say this in human terms, but let's say a deer or something. It grows to a certain size, and now rather than putting its energy into growing, it puts its energy into reproducing. So that's why they stop growing when they reproduce. But there's plenty of things that have indeterminate growth, that continue to grow throughout their life. So fish are an example, snakes, most reptiles are indeterminate growth things. And so the question might be, well, why do these organisms continue to grow? Why would you want to be a largemouth bass that is this big versus this size, right? And the answer has to do with the number of eggs that these fish will produce. So this is with rainbow trout, steelhead, and what you can see is, look at this graph here. This is fish length in centimeters. So you got about a foot long here, 2 feet, and 3 feet. And then this is the total number of eggs produced. And what we see is that as you get bigger, you have more and more eggs. So if you were to stop growing if you were a female fish that were stopped growing at 50 centimeters, you're only going to have about 3,600 eggs each time that fish reproduces. But a individual that is 80 centimeters is going to have way more eggs and be able to really reproduce much more efficiently and have many more babies. So this indeterminate growth strategy is really important when the number of babies that you can have is determined by your size, right? So if these are both female largemouth bass, this one is going to produce so many more eggs than this one would be able to. So I think this life history strategy thing really is interesting when we talk about Finding Nemo. I don't want to ruin the movie for Finding Nemo, but this is what actually would happen if the first couple of minutes of Finding Nemo were to happen. So if you remember in that movie, spoiler alert, one of the parents dies, right? So you've got 2 clownfish living in a sea anemone, right? They have some babies that the eggs are down here underneath the sea anemone, but you've got a male and a female. A barracuda comes along and eats the male. and then you're left, and it turns out it eats all the eggs too. But what you're left with then is one big male fish and then his son, Nemo. So you got Marlin and Nemo, right? The thing is, this isn't really how this would have played out. What we generally see with clownfish, and there's a variety of strategies with different species of clownfish, but the biggest individual in the anemone will be the female. And then the male will be slightly smaller. Now, what happens then is the female is generally older. And so what they do is when they have babies, they have all the babies are born male. So you would have had, her name was Coral, Marlin, and then a bunch of Nemos, basically. And what happens then is if this male dies, if he gets eaten by a barracuda, that's fine because then Coral can just mate with Nemo. But that's not what happened, right? Coral died, the female died. So what would have happened is that Marlin would have grown into a female and then mated with Nemo, the next largest male. And this is kind of taking this idea of this indeterminate growth to a really weird scenario, but it's what actually happens with clownfish, right? It pays to be bigger for the female to be bigger. The more bigger the female is, the more eggs she's going to produce. So in this scenario where you have the largest female getting taken out of the population, this male, because he is the biggest now, would grow rapidly, turn into female, and then mate with any other male. And that male, the only male left, would have been Nemo, which would have made a very different Disney movie. But hope you enjoyed that last little tidbit, and see y'all later.